Welcome to Space Repo, your guide to the cosmos. Neutron stars are already the champions of density in our universe. Imagine taking the mass of our Sun and crushing it down into a sphere just a few kilometers across. A single teaspoon of this material would weigh billions of tons. These objects are the collapsed cores of massive stars, the remnants of supernova explosions. They are cosmic fossils, spinning at incredible speeds, and are marvels of physics in their own right. But within this family of extreme objects, there exists a subclass that takes cosmic terror to an entirely new level. We're talking about magnetars. These aren't just dense, they are deadly, possessing a power that defies easy comprehension. While a neutron star is a fascinating object of study, a magnetar is a cosmic monster, a true contender for the title of the most dangerous object in the universe. So, what makes a magnetar so terrifying? The clue is in the name, magnetism. A typical refrigerator magnet has a magnetic field of about 50 Gauss. Earth's magnetic field, which guides our compasses and protects us from solar wind, is about half a Gauss. Even the most powerful magnets created in a laboratory on Earth struggle to reach a few dozen Tesla, which is tens of thousands of Gauss. A standard neutron star already has a magnetic field millions of times stronger than anything we can produce. But a magnetar leaves all of them in the cosmic dust. A magnetar's magnetic field is, on average, 1,000 trillion times stronger than Earth's. That's a 1 with 15 zeros after it. This isn't just a quantitative leap, it's a qualitative one that changes the very fabric of reality around the star. Let's try to put that power into perspective. If a magnetar were to suddenly appear halfway to the moon, its magnetic field would be strong enough to wipe the data from every single credit card and hard drive on Earth instantly. It would be a global digital apocalypse. But that's just the beginning of its destructive capabilities. The real danger lies in how this immense magnetic field interacts with matter. At a distance of 1,000 kilometers from a magnetar, the magnetic forces are so intense they would become lethal to a human being. The force would be strong enough to distort the electron clouds of your atoms, essentially tearing your body apart at a molecular level. The iron in your blood, which is essential for carrying oxygen, would be ripped from your hemoglobin molecules. You wouldn't just be pulled apart, you would be chemically disassembled. This process is called diamagnetism, where the magnetic field induces a counterfield in the atoms of your body. The magnetar's field is so strong that this counterforce becomes overwhelmingly powerful, overcoming the chemical bonds that hold you together. It's a demise so exotic and complete it sounds like science fiction. Magnetars are born from specific types of supernovae. Not every massive star that goes supernova will produce one. Scientists believe that a star must be spinning incredibly fast just before it collapses. This rapid rotation, combined with the churning, convective motion within the star's core, acts like a cosmic dynamo. It amplifies the star's initial magnetic field to these insane, mind-boggling levels. The process traps the magnetic field within the newly formed neutron star, creating a magnetar. But this incredible magnetic energy can't stay contained forever. The magnetar's crust, made of a crystal lattice of atomic nuclei, is under immense stress from the shifting magnetic field lines beneath it. This tension builds up over time until it reaches a breaking point. When the crust finally cracks, it releases a monumental burst of energy in the form of X-rays and gamma rays. This is known as a starquake. These events are so powerful they can affect our own planet from thousands of light years away. One of the most famous events occurred on December 27, 2004. A giant flare erupted from a magnetar named SGR 1806-20, located about 50,000 light-years from Earth. In just 1/5 of a second, the flare released more energy than our Sun produces in 150,000 years. The wave of gamma rays and X-rays slammed into Earth's upper atmosphere, partially ionizing it and disrupting some long-wave radio communications. Satellites were saturated with radiation. And remember, this happened from a distance of 50,000 light-years. If this magnetar had been within 10 light-years of us, the flare would have likely triggered a mass extinction event. The energy would have stripped away our ozone layer, exposing the surface to deadly levels of solar and cosmic radiation. The sheer intensity of the radiation would have been devastating for life on Earth. It serves as a stark reminder of the violent and unpredictable nature of the cosmos. The physics near a magnetar is a realm where our conventional understanding breaks down. The magnetic field is so strong that it can affect the vacuum of space itself. According to quantum electrodynamics, the vacuum is not truly empty but is filled with a sea of virtual particle-antiparticle pairs that pop in and out of existence. Normally, these particles are unobservable. But in the presence of a magnetar's field, the vacuum becomes birefringent. This means that light passing through it behaves as if it's moving through a crystal, splitting into two polarized beams. Space itself acquires properties, warped by the sheer magnetic might of the star. Even photons, particles of light, can interact with each other in these extreme conditions, something they do not normally do. A magnetar's environment is a natural laboratory for testing the limits of physics, a place where the laws of nature are pushed to their absolute extremes. Fortunately for us, magnetars are rare. Astronomers have confirmed only a few dozen of them in our Milky Way galaxy, and they are all at safe distances. They are also short-lived phenomena, at least on a cosmic timescale. The intense magnetic field that defines them is also their undoing. The energy released during starquakes and flares causes the magnetic field to decay over a period of about 10,000 years. After this, the magnetar settles down to become a more ordinary, though still incredibly dense, neutron star. Studying these objects helps us understand the fundamental forces of nature. They provide insights into the life cycle of stars and the violent processes that shape galaxies. Every flare and flicker we detect from these distant monsters is a piece of a puzzle, helping us build a more complete picture of the universe we inhabit. From the iron in your blood to the very fabric of space-time, a magnetar has the power to tear it all asunder. They are the ultimate cosmic predators, a testament to the raw, untamed power that lurks in the dark corners of the universe. Thank you for joining us on this journey at Space Repo. If you found this exploration of cosmic dangers as fascinating as we did, be sure to subscribe and join our community. There's always more to discover.